Recording then, and wish everyone a happy garbage day. The last Tuesday before break. Hooray! Yes. So thank you to those of you who turned in your outlines. I'm gathering the dates and trying to figure out as quickly as I can when people are going to present. Spoiler alert, most of you chose that you wanted to go last. Not everybody can go last, so I will see what I can do based on everyone else's combination of availability. Please keep in mind that you do need to plan to present in person. So that's the only way that I can make this work. I'm doing the hybrid thing out of convenience, and so folks who are sick have an option to attend, but I don't see a way in which we can have a fair playing field with some people on Zoom and some people off in terms of the presentations. Hey, another person. So I will let you know when my feedback on those is available. Another announcement, Wednesday, tomorrow, I have to end office hours early. I got pulled into a university-wide meeting that they wanted me to be there specifically, so I said, okay, I can go and do that. Next week, you're probably not going to hear from me. I hope you enjoy your time off. Does anybody do anything fun? And sleeping more and laundry counts, by the way.
Oh, then yes.
Yes.
Lots of fun things.
I'm looking forward to not setting an alarm. That's what I'm looking forward to, because it's spring break for the kiddos at school too.
Oh, nice. I'll be home in Wisconsin.
Oh, Wisconsin.
So I'll be bringing Pam home again. So we'll have 3 cats and a dog and 2 people in our 1,400 square foot house.
Well then, that's a lot of fur.
Yeah.
Yeah. Anyone on the Zoom doing anything fun? No? Okay, fair enough. Next thing then, after break, you have a formative assessment. That is available already, so you can start it or get it done or ignore it until the next after break, your choice, whatever. You should be able to answer most of the questions, I think probably right now and then after this week for sure. Let's see, we have another day where we're going to be stuck on Zoom only because we're being kicked out of our classroom, so that is the Thursday afterwards. And this morning I just put up homework 3. So this is an online homework. It is over the accelerated time models. So example 3, the MLM side, that's the last online homework. After that, it's project time. So you'll be spending time fighting with your own data sets and hopefully learning the ins and outs of what you came to do. So those are my updates for the moment. Any questions on that? Nope. Okay. Then let's see, let me get rid of that. We were looking at latent factor stuff, right? That sound right? Okay, so let me reorient us to what we're trying to do here. The example that I'm showing you is going to demonstrate 2 different versions of a multivariate analysis of growth curves. So you can think of the multivariate aspect in 2 different ways. The first way is indicated by this picture. This is where we're building towards. This is the idea that we have observed measures of some latent construct at each occasion. We have multiple occasions. And so rather than measuring change within each observed indicator, what we're trying to do is first build a latent factor for what the trait would be at that occasion, and then use these upper level intercepts and slope factors to predict change in the latent factor. So we're thinking of this conceptually as one thing that's changing over time, and that one thing is measured by 3 observed variables. Okay, with me so far? Okay. Now this seems fairly straightforward, like in theory, but the nitty-gritty of it quickly gets very complicated. The first thing that we have to do, though, is ensure that we have evidence that we're measuring this trait in the same way by these indicators over time, that essentially it is the same trait that has the same meaning. Otherwise, it makes no sense to see if something that changes over time grows. Like conceptually, it's not the same idea. So that leads us down the road of measurement invariance constraints, which may be familiar to some of you and brand new to others. So who has had this before in their lives or their coursework? I know you have. Let's see, Hillary has. Taylor, have you had any SEM stuff yet? Nope. Okay, Dan has. Nope. All right. Ahmed has. Riley, have you? I think you have. And I'm pretty sure Ryan has too. She was in the last SEM. So, yeah. Okay. So we have most folks are familiar, but not everybody. So would it be helpful, even if you're familiar, for me to go through this a little more slowly and gradually so that we're all kind of staying on board? Okay, that's what I was thinking. Yes, big nod. So I should assume that you don't have perfect recall of a class you took a full year ago, too. That's what I'm learning.
You shouldn't expect me to have perfect recall of anything ever, I don't think.
Yes, and I agree with that. I'm sort of being sarcastic that as instructors, it's kind of like when students have questions or if we see evidence that they don't know something that we've covered, it's like, we covered this. And it's like, no, we may have covered this, but it was a year ago and there's no perfect recall of anything. So I get it, trust me. I don't know what I did yesterday, like, let alone, what we talked about a year ago. So we'll start at the beginning. So I have 3 measures of what is supposed to be cognitive functioning in older adults. And these things have a correlation pattern that indicates they're probably indicators of a common latent trait. I'm going to call that cognition. For those of you who study cognition, I'm sorry, I'm glossing over a lot here, but that's not the point. It's basically just like, X1, X2, and X3 from our perspective here. So the first set of analyses then is configural invariance. That's where we let each of the measurement model parameters be whatever they want to be. Then we, in successive models, apply constraints to force things to be the same over time. We see how much worse the model fits as a result of those constraints. The goal is not worse. So we're starting with the most complex model, and we're taking away parameters by forcing things to be the same. So it's not going to fit better, but the goal is not worse.
Is it kind of similar to the way we thought about like building our models last semester too, where like we start with our unstructured, saturated model and then try to like take things out until we get the best fit with the least amount of parameters? Or is it?
Yeah, I would say there's an analogy there.
Okay.
The most direct analogy is in Unit 6, where I had like 6A, 6B, 6C, 6D
Yeah.
handouts, that giant mess. The very last thing we did within each family of models was compare against a saturated means model to see if the fixed effects were modeling changed appropriately, and then compare the random effects against an unstructured model to see if they were a close enough approximation.
Okay.
This is like that,
Okay.
I would say. And then we get to the part that we actually care about, the growth of the factors, or the curve of the factors. Factor of curves is the second half of that, but okay. So this is wide data. That's one thing to keep in mind, because it makes everything look very different in terms of the code, and there's no clear demarcation as to what is level 1 and level 2. So the first set of models here, I would not even consider growth models. They're factor models. We just happen to have a factor that represents 4 different occasions as opposed to 4 different kinds of factors. So conceptually, it's not different than a standard CFA model. And I should mention, by the way, that these are reasonably continuous indicators, and so that's why I'm fitting the confirmatory factor analysis version, which is analogous to linear regression, where we have linear relationships between the trait and the indicators. If these things were like, 5 category scales or binary or something else, then we want a version that incorporates a link function. So the analogy to that in the SEM world is something called item factor analysis as opposed to confirmatory factor analysis, which is essentially factors predicting logits or probits instead. So any kind of outcome can be used with these models. If you're planning on doing something like this and you don't have continuous indicators, there's another chapter after this one. So I think, hey, come back. My screen's just left. This same book has another chapter in it that covers those models for categorical outcomes. So that would be a resource for you, and you can also ask me. So let's see here, names. What do we need to remember about this command?
Less than 8.
Less than 8 characters for each name. What is happening when I have a dash in between?
Covers through.
Yeah, it's filling in the missing numbers. So pros 2, pros 3, pros 4 is what this implies. And these have to be in the order in which they are in your spreadsheet. So your CSV file or your .dat file. Use variables then indicates which ones are actually going to be in the analysis. So I have all 4 occasions times 3 indicators, so there's going to be 12 altogether. Let's see, in terms of options, this is a general type. Other types are 2-level, 3-level, mixture, trying to think of others. Type equals random, there's a few others, but general is what this one would fall under. We're using robust maximum likelihood. Why is that important in thinking about model comparisons?
So it changes your if you do likelihood ratio tests or log likelihood.
Yeah, they have to be done differently this way. So there's an extra step. Normally, we just take the difference between -2 log likelihoods, and that is the chi-square. In this approach, you also have what's a scaling correction factor that has to be taken into account in the computation. So the test statistic gets rescaled by that, essentially. So it's not a complicated formula, but it's annoying to try to do like manually. So I built a spreadsheet to do that, and if you use Lavon to fit these same models in R, the ANOVA function will do model comparisons for you using MLR. So that's what I would probably recommend. Residual means show me why the model doesn't fit. So this is essentially going to give me the discrepancy between each mean, variance, and covariance that are in the data and what my model says they should be. So if we end up with poor fit, this is where I will look to see why. Mod indices also can be used to troubleshoot misfit. In our context, what we're going to look at is, are there any of the constraints that, if released, would significantly improve the model? Because when we test a bunch of constraints at the same time, like you could test 10 things and have a non-significant result and be like, yay, I win. But it could be the case that like 9 of them don't want to be different, but 1 really does, and that 1 is getting washed out by testing 10 at the same time. So to prevent that from happening, we'll look at the constraints, this section, to see if any of the constraints individually are problematic. Some things want to be different. STDYX is a standardized solution. We're not going to be dealing with that one very much, but that's where you would look to get standardized factor loadings as well as correlations instead of covariances. And Tech4 builds correlation matrices of our latent variables, which will be helpful to summarize the output a little more succinctly. Okay, that's the overview of the data steps. So from this point forward, like all of this is going to be the same. It's just the model part that's going to change. Any questions thus far? Okay.
Which code is the unstandardized? I forgot.
Say that again?
Which code give us the unstandardized?
Unstandardized is what you get by default. If you want other forms of standardization, you have to ask for it. So there's a couple different options. This version standardizes both the X side and the Y side. So every variable in your analysis turns into mean 0, variance 1, so that everything is fully in standardized mode. You can also standardize just the predictors, which is STDX, or just the outcomes, which is STDY. And I think there may be a few other permutations in there, but those are the ones that would be most useful. Does that help?
Oh, sorry.
Go ahead.
In the residual thing, why do you put the 6.635? Like, is that a magic number? What's that about?
This looks like an arbitrary number, but it's not. This is the critical value for the change in the chi-square for model fit at the 0.01 level. That's why. So I'm only asking for things that would help the model significantly at alpha 0.01 as opposed to 0.05 or some other place. 3.84 would be 0.05 instead.
You said that's the chi critical value?
Yeah, it's the critical value for a chi-square to be significant at the 0.01 level for 1 degree of freedom, because each of these individual constraints is going to be one thing at a time in mod indices.
And then what happens if it says no model fit indices for 6.35?
Great question. So it will use this as a criterion and not spit out anything that's under it. And so if it says that, then that's what happened. And if your model still doesn't fit, though, then you may have to lower this to get it to spit out something that you could take advantage of. So that has happened before, especially in invariance testing, where everything is still significantly worse after putting constraints on, but you can't figure out why. That is a very tricky situation to be in. Okay, other questions? All right, then configural invariance model. I doctored this picture to make it work for our example. So we only have 3 indicators instead of 4. That's why I X'd out this 4th box. We have circles indicate latent variables. So this would be, their terminology is eta. I would call this the factor. And so these are the idea of latent variables that are then predicting the boxes, which are observed indicators of block design, digit symbol substitution, and prose recall. So these directed arrows are slopes, but in this context, we're going to call them factor loadings instead. It's a semantic distinction. The term factor loading is applied when the predictor is latent rather than observed. If the predictor is observed, like if this were a box, then this would be called a slope instead. And in this framework, slopes are also known as paths. They're also known as direct effects. So there's like 17 synonyms for what this arrow represents, depending on what you want to call it. Any others? Is there a DAG terminology for this?
Just the effect.
The effect?
Causal path.
Causal pathway? Yeah, I'm not going causal. That's just not happening in my world. But the key idea here is that the factor is the predictor. So this is a multivariate equation where this factor is predicting these three things at the same time. And same here and same here. So the arrow going into itself, that is a diagramming convention that indicates a variance is being estimated. So in their way of setting up the model, they estimated variances. I decided to fix them to 1 instead so that we could look at correlations among the factors a little more readily. So this idea, what we're talking about here, is under the idea of model identification. Factors are imaginary. So to make this work, we have to give these factors a scale. And how that works in practice is one of two ways. Each factor needs to have a mean, each factor needs to have a variance. You can either fix them to be known constants. So for instance, a very common solution is to fix factor means to 0 and variances to 1. That's how it works in IRT as well for a lot of the cases. Or you can borrow the scale of the factor from one of your indicators by instead fixing one of these loadings to 1 and letting the variance be estimated. So it doesn't matter in the grand scheme of things because there's no wrong scale. These are imaginary. A standardized scale for your factor can be convenient if they're not being predicted. But once we get to the point where we have a growth model on here, we're going to switch the method of identification, which switches the scale. So the analogy that I use in my SEM class, and no, I'm not going to sing at you today, you'll have to take the class for real if you want to hear that version of it, is like when you play music, you have to select the key of the song that you're going to play. And so once you know what key it's in, then you know how to arrange the notes, like a half step here, 2 steps here, etc. If you change the key, the pattern stays exactly the same. You're just on a different scale. So I think of it that way. It's like you're setting the key of your model when choosing this method of identification. And it doesn't matter which loading you would fix to 1, they result in equivalent fit. It's just this is in the key of this variable versus the key of that variable versus the key of that one. So they chose a different method of identification. I'm fixing it. These things, these 2-headed arrows, remember what these are?
Covariances?
Yep, factor covariances, so they get to be related to each other. Covariance meaning unstandardized correlation. And the stupid triangle thing. This is a diagramming convention that's used to introduce means and intercepts as explicit things in the diagram. Where it comes from is if you were to write out like a regression model using matrices. To make it work, you have to have a column for the intercept that would then multiply beta 0, and that should be just a column of 1s. So this triangle is meant to be the column of 1s. That's what it's representing. So it will create intercepts and means. It's not a variable, it's a constant, which is why they had to come up with a different shape. And I don't do the triangles in my diagrams because I think it makes it look unnecessarily cluttered. But what it's doing then, these arrows into it that look like pitchforks, kinda. Am I crazy, or does this not look like a pitchfork?
They do.
Like they look evil, you know? Or what is it like?
Trident?
Yeah, that's what I'm thinking of, like a sea monster, like in The Little Mermaid or something, that has like a spear. So yeah, the triangle is attacking these boxes right now through what are going to be intercepts. So each of these boxes then starts off with its own intercept, and then the contribution of the slope, and then the 2-headed arrow down here where they're using theta for it, for whatever reason, is meant to be residual variance. So whatever's left over in that indicator that's not related to the trait. So it's the same idea as residual variance being left over, except that just like we would say random effects don't explain things, I would say these factors don't really explain things either. What you're saying is how much of the variability in each of these indicators is attributable to a latent factor, and I would say it that way, versus how much is not that. So for the first one, for instance, like block design, residual variance is whatever creates variability in this task that's not cognition. Some other trait that's in there that we don't know what it is. Okay, then the lines going from the triangle up to the factors then, I took those out because I changed the method of identification for each of these factors to have a 0 mean. And whereas previously they had estimated it and left one out. So 6 of one, half a dozen of the other, but I wanted to borrow the picture. Okay, I think I hit everything that's in there. I know that was a lot of words. Questions? What is tau again? They're using that for intercepts. So I don't know why. They have a whole different notation scheme, and several of the terms involve things I can't draw or pronounce, so I'm just not here for that. Okay, so first things first then. By, that's how I make factor loadings. So T1 is the name of my first latent variable, T2 is the second, T3 is the third, etc. And the stars here indicate that I want the loadings to be whatever they want to be. Like they're estimated, and they're not constrained, they're not held equal, they're nothing. They all get to be what they want. In M+, stars mean estimated. In Lavaan, however, stars means fixed. So it gets confusing when you work back and forth across programs. You don't have to type the stars, they're a default. Except for the first one. Thank you for reminding me of that. Yes, you do remember that. Yeah. Are you troubleshooting models that didn't converge? And remember that rule? Yeah. Yeah, so this is an implicit default thing that you wouldn't know unless like someone told you or you read the manual. The M+ default identification is that the first indicator, so that's the term that we use for these outcomes, is indicators of the trait. The first indicator's factor loading is by default constrained to 1 because their default identification is first loading constrained to 1, factor variance estimated. So to override that default, I do need a star here, as well as this one, like the first one in each of these. I would not have to type it out here. And note, everything ends in a semicolon. Things in brackets then next, these are the intercepts. So regardless of how many factors are predicting these indicators, each indicator only gets one intercept, the same as in like a standard regression model. So they get to be whatever they want as well. Indicator residual variances is what I'm asking for here. So the amount of variance in these observed indicators due to not the factor, they get to be whatever they want as well. So essentially every box here is going to have 3 parameters in this model. It's going to have an intercept, which is the expected outcome when the factor is 0, when it's at its mean. It's going to have a factor loading for how well the trait predicts that indicator. And it's going to have error variance for amount of variability that's not the factor, some other thing. Last but not least, an extra piece of the measurement model that is not normally here, except in longitudinal, is to allow covariances of the same indicator with itself over time. So block 1 gets to be correlated with block 2, gets to be correlated with 3 and 4 because it's block design. So that's just a default that people sort of leave in no matter what. It looks like many of these are non-significant in this particular data set. If I wanted to sort of make my model more parsimonious, I could go through and try to get rid of the ones that aren't needed, but I decided not to bother with that. Most of the time, folks don't. So this part, from here to here, is what's considered the measurement model. The measurement model dictates how observed outcomes relate to their latent traits. Measurement model has loadings, intercepts, residual variances or error variances, those are synonyms, and any residual covariances. This part, this is the structural model. Structural model concerns things about the factors, their means, their variances, and their covariances. So in brackets then, I'm fixing all the means to 0 for identification. So my model is in the key of Z, give or take. And I'm fixing all of the factor variances to 1 as well. And all the covariances are free. So there's 6 possible covariances being estimated with this line with width here. All right, backing out. Did I forget anything? I don't think so. Okay, any of that you want to ask about or hear again? And no, you won't have a homework on these models, but you're welcome to use them for your project if you wish.
Okay, I have one question. So when you say that the intercepts can be whatever they want to be, is there some sort of like time centering, like when we were doing this stuff before, obviously like the intercept would be at time zero, but like what does an intercept mean in this model, I guess?
Okay, the intercept means the same thing in any model. It's always the expected outcome when your predictors are zero. In this context, the predictor is the trait. And the trait is scaled so that it has a mean of 0 and a variance of 1. Traits are assumed multivariate normal. That's something that you can find it occasionally in software, but it's very rare, and that's much less developed. So we just sort of assume that these traits are multivariate normal. In practice, they're not going to be, to the extent that they're not well measured. Like, you'll have floor and ceiling effects, they'll have skewness and stuff that is a result of limitations in how much information you have to estimate a trait level. So I think I lost the plot here. Did I answer your question, or did I get halfway through it and lose the plot?
No, that makes sense. It's the trait it's at 0 for the trait, not 0 for time or whatever.
Exactly. And so what ends up happening is, because we set the mean of the trait to 0, it's like we centered it. So the intercepts become the expected outcome for the average person, which is just this indicator's mean. For that reason, some folks call these indicator means instead, because that's what they become. Do not do that. They're intercepts. The mean is only a consequence of the factor mean being 0 as a method of identification, and that is not going to be the case like 5 pages from now. It's a 25-page handout. We're going to be here a while. Okay, other questions or things I forgot to say? So our first step then is to make sure this thing fits, because it doesn't make sense to go forward if it doesn't. We want to demonstrate that the patterns of relationship among these indicators that our model predicts is accurately representing the patterns of relationship that are in the data. More specifically, we want to make sure that all of the means for these indicators are being recreated by the model. They should be, as long as we have each intercept estimated separately. All of the variances, they should be, so long as each indicator gets its own residual variance, and all of the covariances, and that's the tricky part. So we are saying, for instance, that the only reason why this box and this box are related is because of this in common. They're not related otherwise. And for things that are on different factors, like the only reason this box and this box are correlated is because the traits that they measure are correlated. That's what we're saying. So we're predicting the correlation pattern from this model. And in the SEM class, I go into that into more detail, but that's the main idea. So to the extent that the actual correlations don't match the ones that are implied, then we have a problem that we need to solve first. And it is the correlations that it comes down to in terms of misfit for these kinds of models. Means and variances are usually saturated. So that's our first stop, is to make sure that that happened. So this is us, the HO. H1 is the saturated model. So H1 is the best the data can be, the tallest they can be. It means it's essentially fitting a model where you're directly estimating all of the means of your variables, directly estimating the variances, and directly estimating the covariance. Last semester, we called this saturated means unstructured variance model. That is the same thing. And I used to have a very difficult time remembering which was which, until one day a student asked a question that solved it forever. Yes, you're going to hear this story again. Nod to Lindsay, back at Nebraska, when I was doing office hours in a giant computer lab, helping a bunch of people at the same time. She pokes her head up and she says, "Am I the hoe?" And I was like, "What?" She's in M+. Am I the hoe or am I the H1? And I'm like, "Oh, yeah, you're the hoe. Go ahead." And so after that, I never forgot. Just remember, you're the hoe. And whenever I go to Kohl's and pick up an online order, on my sack has a tag that says HO. And so I'm like, I'm the hoe because of Hoffman. So I'm really the hoe. So yes, this is your model, whatever you said it was going to be. H1 is always the best one. So the goal then is to see how much shorter our model's likelihood is than the best one, and hope that it's not that much shorter. These are the scaling factors that I mentioned earlier that have to go into that computation. One indicates perfect multivariate normality of the observed indicators, and so this is used to correct for the extent of non-normality in terms of the fit statistics and the standard errors as well. So this likelihood ratio test comparison, fixing these two things, is actually done for us right here. So 27.7 is the chi-square test that tells us how much worse our model fits than perfect. So we talked about this last time, but just to drive home the point, this test on 30 degrees of freedom is non-significant. Good thing or bad thing? This is a good thing. So this means not worse than perfect. That is very rare in practice. I can count on one hand the number of times I've had model fit be non-significant. So what folks tend to do is also use, or just ignore this and move on, and use other indices of fit. And there's like a bunch of these. So there's a whole long history of this. I don't want to get into the weeds on this. The evidence suggests that this model fits well by every standard. So RMSEA, here's a pro tip on how to remember which way these go. If the name has the word error in it, you want it to be as close to 0 as possible. If the name has F for fit in it, you want it to be as close to 1 as possible. So that's how I remember it. So RMSEA is how much worse than perfect relative to how many degrees of freedom are left over. It's 0, so as good as it gets. Our SRMR is another one that works that way. This is how wrong your correlations are on average. 0.01 is pretty darn good. And CFI and TLI are different. They instead start from what's known as a null model, in which you're estimating all the means and all the variances, but forcing all the covariances to 0. And then this is saying how much better is our model than that crappy one. And so it's this, a lot better, perfectly better. TLI goes above 1, by the way, so it's not normed in that way. And you can ignore this one because this is null versus saturated, which has nothing to do with this. So far so good. So these are the factor loadings. We cannot compare them directly because these are in units. So for every unit increase in my factor as the predictor, my block design score should go up by 6, my digit span score should go up by about 10, and prose recall goes up by about 3. So these are outcomes of the same predictor as a factor. What we can do is kind of eyeball the trends, though, over time. It looks like these are relatively comparable. Same thing for the others. So these are the loadings that we're going to constrain equal next to see if they can be constrained equal over time and not hurt the model fit. Factor covariances is the next thing we get to see, the widths. So it looks like my factors are pretty highly correlated over time. Residual covariances vary. So block design has a bunch. Digit has some. Prose has a bunch. So we let those be. Here's the factor means. Remember what 999 means? Is that a number? Nope, it's missing data because you can't divide by 0. Indicator intercepts. These are the expected outcomes when my factor is 0. In this model, my factor mean is 0, so these are the indicator means directly. And we looked at these patterns, and it looks like they're all going down over time. So it looks so far that the idea of a common factor and that factor changing over time is a reasonable thing. If some of these went up and some of these went down, we'd have a problem. Then we'd want to do things a little bit different way. Factor variance, fixed to 1 as well. And indicator leftover variances, this is the amount of not the factor in each of these things. Okay, so words about what's happening next. So the steps for invariance testing, as it is known, and by the way, I hate that word, I'm sorry, that's what people use. And you would think that it would be invariant and variant, right? No, it's not. The alternative to invariant is non-invariant. That is how people talk. And at that point, my brain breaks, and I'm like, invariant means same, non-invariant means different. And if you're familiar with the term differential item functioning from the IRT world, it's the exact same set of ideas, but that means non-invariant as a starting point. So invariance testing starts from the idea of all the same. Non-invariance differential item functioning starts from the idea of all different. So more confusing terminology, unfortunately. So I'm taking pity on you here, as I indicated last time, and using colors to indicate what has changed in the code and how that shows up in the picture. So the first thing that we're going to do is try to constrain the loadings for the same indicator to be the same over time. So pros still gets a different one than digit still gets a different one than block design, but it's like block at 1 has the same loading as block at 2, as block at 3, as block at 4. The way that we're going to do that is by labeling these things, creating constraints. So BL stands for block loading, DL stands for digit loading, and PL stands for pros loading. So I typed BL refers to this loading right here, and here, and here, and here. So the end result of it is going to change it from having 12 loadings in total to only 3. A block 1, a digit 1, a pros 1. So the question we're answering is, does the indicator relate to its latent trait the same way over time? That helps us to understand whether conceptually it's likely that it is the same trait over time. If these patterns don't hold, then it's harder to make that argument that it is one thing that's growing as opposed to the thing itself shifting shape. What was it? Trident?
Trident, yeah.
Yeah, okay. Trident is a kind of gum too, right?
Mm-hmm.
Okay.
I have a question.
Yeah, please.
So previously you said for those factor loadings, you said the correlation is pretty high. And then I remember like when I take the SEM class, you said if it's the correlation is 1, it's game over, right? So if that correlation is very high, is that a good sign or bad sign here?
I think it just is what it is. It looks like there's a lot of commonality in the trait over time, like a strong intraclass correlation is the way that I would think about that. If your factor correlations go above 1, then you'll have to do something to rein them in, put a type of constraint to keep those under. I have an example of how to do that in the download packet. Let me see here. Go over to the original files. So this is what I'm reporting in this handout. I have an example of constraints on standardized factor loadings in these ones here because I was doing some different modeling and ran into those problems. So I thought I'd leave those in there. If you need to implement a constraint like that to keep your factor correlations under 1, what you would need to do is essentially recreate the correlation out of your model parameters using labels and a new statement, and then use model constraint to force that correlation to stay under 1. I have examples where I've done this I can send you if this is something you want. Just send me an email to remind me that we had this conversation. Okay, other questions? All right, so we had 12 loadings, right? How many did I say that we have now? 3. We're not done yet, though. If we just did this much and let it go, we would be enforcing both a measurement constraint of how the factor predicts each of these indicators, as well as a structural constraint, because we're up to this point, the factor variances would all be forced to be the same. So we need to free factor variances at the other occasions. I am keeping the first occasion's factor variance fixed to 1 for identification. So essentially what we're asking is, were any differences in the loadings over time reflective of differences in the factor variance over time? Once we let the factor variance change over time, then is it the case that we can say the way the trait relates to the outcome is the same across time? So we have to both put constraints and then free things in the structural model at the same time. So that's why I have yellow highlighted stars up here. And that shows up in the code by changing the @1s, which is a fixed parameter, to stars to indicate that I'm estimating the factor variances at the subsequent occasions. Now, one thing about choices for model identification, This is not the most common way to do this. But the alternative is to continue with a marker item, like for this one would be fixed to 1, for instance, and then estimate all the factor variances. So let me show you what this would look like. The alternative way would be like that. And then we would have a star down here. I don't like this. Can you guess why?
I feel like the other way communicated what was happening in the code a lot better.
The other way is perhaps more transparent. Let me ask you the question a different way. Is 1 equal to 1?
No, we don't have the scale of
Yeah.
what things are.
Exactly. So we're doing this to identify the model, but at the same time, then we can't test whether the block design loading wants to be different across time because we're forcing it to 1 at each occasion. So we're not testing invariance on all the things we could if we use a marker item, so that it's suboptimal, because if this should be different, the rest of our model is all going to break because of that, the constraint that shouldn't be there. So that is why whenever I do any kind of invariance testing, I don't use marker items. Come back. And instead, I use the first factor as the reference, essentially. Keep its mean to 0 and its variance to 1. There we go. And then I can test all the measurement model parameters. So we're doing it that way on purpose. Okay, so then in total, we saved 9 degrees of freedom, is the way to think about it in terms of estimated parameters, by forcing the loadings to be equal, but then we had to give 3 of them back to estimate these factor variances. So that means the net change is 6 relative to the previous model. So the first piece of output that we get here is still the test of model fit. This doesn't answer the question, though. This just tells us, is our model not worse than the perfect one still? What we really want to know is, did we make our model worse by putting on these constraints? Let me get the spreadsheet that goes with this. Maybe. There it goes. It's thinking about it. Okay. So I'll go in here to show where I got these numbers from. So the way this works is that you would input your log likelihood, because that's what M+ is doing. You would input your scale factor. You would input the number of estimated parameters. It's called free parameters, meaning free to be, not 0. Then this computes twice the difference in log likelihood, so this would be your regular test statistic. However, then we have to compute a difference in the scaling correction factors, then compute a rescaled version of this test. So this is the column that you're actually reporting. So by taking away 6 parameters, our height changed significantly. So the test statistic for this model comparison, this likelihood ratio test, is 15, p-value is 0.02. Good news or bad news? Yeah, this is bad news. It means that one or more of the constraints made the model unhappy. So do I take my ball and go home? Nope, we got to figure out which ones it is. So we're heading towards partial invariance, meaning some of them can be the same and some of them can be different. So this is where we would look for output that helps us guide things. So model modifications, this piece of output is towards the very, very end of your M+ output file. I have only put in the relevant parts right here. So what this is telling me is by statements refers to loadings, and I've only printed in here the ones that are relevant. So T4 by pros 4. We already have a factor loading for that. It's not telling us to add one, it's telling us to let it be different. So if we let the loading for pros be different at the last occasion, our model rescaled chi-square should get better by 7, and the loading itself will increase by this expected parameter change. That's what EPC means. Putting that together, our test statistic was 15. Half of that was due to one thing. One loading caused half the damage in terms of misfit. So we can let just that one loading be different and see how we do. Now I have a star here because in the chapter where I stole the diagrams and such from, they go through this process in their data, and their model fits significantly worse at various steps, and they're like, it's fine, I don't care, because they argue that because the model still fits overall, that the invariance constraints are fine. That makes me feel a little squishy. I mean, it is still a very well-fitting model, but I'd like to know what it is that's causing the change in fit. So I'm going to show you a partial invariance model. So then in terms of the solution, and this is something you'd want to check in practice to make sure your constraints are actually holding, I've labeled the constraints that we introduced right here. Question, what if we put both in, T3 by pros 4 and T4 by pros 4? We could. I think that in this case, I ended up, I can't remember why I picked this, but this one is the one that I don't think I picked it on purpose. I was highlighting what it means. You could put in any of these things essentially and the same would result. So it looks like, oh, never mind. Scratch everything I just said. If I were an actual YouTuber, I would have cut that shit out. There's my cut noise. I know why. Because these are at different occasions. So pros 4 wants to load on time 2, and pros 4 wants to load on time 3. So these are additional cross loadings that don't make any sense. So this is the only one that makes sense in terms of referring to one of the constraints that we put in here. I should learn how to read better.
Because if we go back to the model, it's like it goes back to the thing that pros 4 is only related to time 3 and time 2 because of its relationship to time 4. Okay.
Yeah, so it wouldn't make any sense to let time 2 predict an outcome at time 4.
Yeah. Okay.
Like that wouldn't be reasonable. So this loading pattern then is going to help the model correlations get closer to what they should be if we let this one be different. Thank you for the question. So then in the unstandardized solution, you'll notice that these are all the same. They won't be the same in the standardized though. So you want to make sure that your constraints were actually implemented correctly. And in terms of factor variance, do you see any trends here? First occasion is 1, second occasion is 1.1, then 1.2, then 1.5. Yeah, going up. People are spreading themselves out, essentially. More variability as time goes on. So that's indicative, potentially, that we would have random slopes for change over time because the variance is changing over time. If the variance was relatively constant, then that would support a random intercept only instead. So we're getting towards that. So let's do a partial metric invariance model next. Let's play find the code. What's different?
In T4, you constrain.
Yeah, PL4. So the pros loading at time 4 gets a different label, gets to be a different estimate. That's what. So I'm giving one constraint back. Everything else is exactly the same. So now we do the same hypothesis test, and the chi-square is down to 4, so it actually improved more than predicted, and p-value is non-significant. We win. Question?
And you compared that model to the configural.
Right. So this comparison is back to configural. I could also do one between the full invariance and the partial invariance to see if it helped, but I'm skipping that step in the interest of time. So yes, we're always comparing back to the last good one. So this is not worse than configural, which means we can say that the way that these factors are relating to their indicators is the same over time with the exception of 1. I can live with that. At some point, people usually ask me, like, how partial is partial? Ideally, you want most of your stuff to be invariant. If you're down to like 1 or 2 things, it's kind of game over. Technically speaking, though, you only need one constraint to make it work, like mathematically, but that's a terrible idea. because then you're really, really dependent on that one thing. So after we make that change, we're estimating one more parameter to do so. You can see that everything is very happy again. So our model fit is back to the level that it was. So it's not enough in practice to say, oh, it's not invariant, like the end. It's like, what's the pattern? So what I would say in terms of interpreting this is that the loading is 3.4 for PROS. At the other occasions, it's 3.9 here. So it looks like PROS recall is more related to the trait at time 4 than at the other occasions. Okay, so be it. Don't have an explanation for that, but I'm sure I could make one up if you want. Okay, ready for green? It's not easy being green. Scalar invariance. Yes, that was a Kermit the Frog reference. Scalar invariance is for intercepts. This one is especially important for longitudinal models when you're going to look at change over time. And this one is also very commonly misunderstood by folks who call these means. We are not saying that the mean of these items has to be the same over time. We're not saying that. We're adding a constraint that the intercept for block design is the same over time, the intercept for digit span is the same over time, and the intercept for PROS is the same, which is why I wrote them in this way as opposed to this way. What we are saying is that the expected value of these outcomes, given a trait score of 0, is the same over time. The expected value of these outcomes at a trait score of 0 is the same over time. We're setting the intercepts equal, not the means. Said differently, we're going to find out if the only reason that it looked like the means were declining over time in each of these is because the factor is declining over time. And once you let the factor decline, the intercepts can be the same. So that's why over here on the picture, I'm adding back in, kind of messily, but tried to make it work. There we go. The path from the triangle up to the factors is indicating that we're getting to estimate their means now too. So we're letting the factors change over time so that the intercepts for the expected outcome at a factor score of 0 can be constrained equal. The only reason the indicators were declining is because the factors are declining. That's our test. So the same idea, we went from 12 loadings down to 9 the first time. We're going from 12 intercepts down to 3, or 12 to 3, but then we have to give back the 3 factor means. So we don't want to enforce measurement and structural constraints at the same time. We're letting the factors change, that way the intercepts stay the same. So now the factors are on the same scale over time. Previously, they were not. They're shared identification constraints. Survey says, did the full scalar model fit worse than the partial metric model? So since we landed at partial metric, that's my new comparison point against full scalar. And survey says, saves 6 degrees of freedom, p-value is non-significant. Hooray! This is very good news. This means that the idea of all these things sort of changing together, being captured by a latent trait, is reasonable. If this breaks in your data and partial invariance becomes very sketchy, stop. You're done. Don't go any further. Because it makes no sense to ask if a trait changes over time if the indicators don't relate to it in the same way with their intercepts. Like, these things go together. If your invariance breaks too much, then you abandon ship, and you could do something like this instead, where you would fit a growth model per indicator and then see how the intercepts and slopes are correlated. So that will be the last set of models. But this didn't break. Yay me. So, questions on that step? Do you understand conceptually why it's important to have indicator invariance constraints at this point? The loadings being the same over time describes how the trait predicts the indicator the same. The intercepts being the same describes how the expected value would change as a function of the trait, and that needs to be the same. If you don't have intercept constraints, then change in factors doesn't make sense and isn't even identified. It won't work. So here's what we end up with. Here are the factor means. These are relative to the key of z. So the factor mean is still 0 at the first occasion for identification, setting the scale of the factors. And then it looks like, lo and behold, what's happening to my factor over time? What do the negatives indicate? Yeah, it's going down. So like if I set this to be 10 or something, like these would be proportionate to that. Like everything is just relative to what you set as your reference in terms of the scale. And so now then, you can see that the indicators have the same intercepts over time. So what is predicted for block design at a factor score of 0 doesn't matter which occasion it is. All we need to know is what your factor score is. I know how you're going to do. Last step is residual variance invariance. This is somewhat debatable in terms of its importance, but in the interest of being, I'd say, conservative, I'm going to go ahead and do it. So now we're forcing the trident-looking things, that residual variances for each indicator to be the same over time, saying that whatever's left over has the same amount of variability. That one, no, it's very unhappy. The reason it is very unhappy is block design at the first occasion and digit symbol at the first occasion. They want to have different variances than at the rest of the occasions. Normally I would do these in one step at a time, starting with the one that has the biggest impact. So this is saying like the chi-square is expected to change by about 22 if we release this constraint. This one would change the chi-square by about 10. I'm going to do both at the same time to save a step. So then partial residual variance invariance is down here with the same conventions. Now let me explain why this code works the way it does. Semicolons. Normally, if you put a label in, it refers to everything that's in that physical line of code. Not just the command, but that physical line. This semicolon essentially shuts off this constraint from applying to anything after it. So I have BR1 as the residual variance at time 1 for block, which is separate from the residual variance for block at times 2, 3, and 4. So it's still constrained at the later occasions, and the same is true for digit symbol. So survey says, does it still fit worse? No, we win. And our fit is back to the previous levels of spectacular fit with the non-significant chi-square. So, yay! So what ended up happening then, in terms of the residual variances? Yep. It looks like block design has more not the factor variance at time 1, and so does digit, than at the other times. This could be something as simple as familiarity with the task. There's probably more ways to get stuff wrong if you've never done something before. That's my hypothesis. So in total, we largely have measurement invariance. We had to free one loading and let pros be more related to the trait at time 4 than the other times. We didn't have to free any intercepts. We still have factor means that look like they're declining over time. And we have factor variances that are increasing over time. So a growth model is a reasonable thing here. Rather than going through and doing structural invariance testing, though, which is where you would constrain the factor variances to be the same, then the factor covariances, then the factor means, I'm going to head into growth model land. So back to your regularly scheduled longitudinal analysis class. This number right here is going to be used in the code next. This is going to allow our latent intercept to be in the scale of z. This is a trick that they used in the textbook. Okay, so here is our first try at a growth model for a latent factor. Y'all ready for this? Yeah, we are. And it's a latent basis one, because why not? So here's the logic. We can't have the factor at the first occasion have a fixed mean of 0 and a fixed variance of 1. Because what's going to happen is that factor is going to be predicted by the intercept and the slope. So it needs to have estimated variance so it can become leftover level 1 residual variance. We can't have it be a fixed number. It'll break it. So to get around that, we're going to estimate the factor variance at all 4 occasions. But we're going to fix the loading for the first indicator block design to what it was in the previous model. That should end up with a lower order factor that's on the same scale as before, but it will have an estimated variance once it's predicted. So this is an interpretational choice that you could make alternative versions of it, but the idea is that we're trying to still keep the same standardized factor interpretation of the scale. All the invariance constraints from before are on there, and I'm using gray because I'm running out of colors that print and don't hide the text. So here's the new part. Here is what it was before, or excuse me, actually no, this is the structural model modified because we're not going to have stuff predicting it. So at this step, let me show the picture. We're finally at this picture right here. So we have lower order factors as the outcomes of the intercepts and slopes. We have an intercept factor that's going to have these fixed to 1. That means that these intercepts that we previously estimated, these means, need to be shut off so that all the changes in mean and variance in these factors are captured up here instead. So we're moving the information about change up to these things by forcing these intercepts to be 0. That way these do the changing instead. We can fix the loadings of the change factor to whatever we want. We could create linear or quadratic or piecewise. I'm going to show you latent basis for this. Okay, so recapping. Factor intercepts is what they're now called because they're predicted. They have to be fixed to 0. Question, can I share one more time why I chose 5.972? Here's why. Because in the solution previously, the 4-factor correlated model, find it again, here it is, the loading for block design was 5.972. That is the loading that resulted when we fixed the factor at the first occasion to have a mean of 0 and a variance of 1. So I want to recreate that. I want that scale back. So by fixing the loading to this, I'm essentially recreating the same scale where the factor has a mean of 0 and variance of 1 at the first occasion in total. That's my goal. That's an arbitrary choice. I could have picked this one or this one, but I'm trying to recreate a standardized factor scale. Does that help? Okay. So these are the lower order factors, as they are called. Their intercepts are fixed to 0. Their variances are all now going to be held equal because I want to force all the differences in variance up to the growth factors too. And I've labeled this resvar. Do you know why? This residual variance, do I mean leftover or do I mean level 1 residual variance or both? Yeah, I mean both. So if you think about these as your outcomes, the variance of your outcomes after being predicted by the factor, what's in the R matrix, these are level 1 residual variances. We're constraining them to be equal over time. We are shutting off the covariances among the indicators that would be in the off diagonals of your R matrix. So the intercept shutting off part is not something we had to think about before. That's new. But we did do this by choosing a diagonal R matrix. We're letting all the residual variances at level 1 be equal. No covariances, because we're saying the only reason they were correlated is because of the intercept and slope factor. That gets us to those. Int and slip, 3 letters. This is an intercept because I set it that way, at 1. This is a latent basis slope. So 2 of the loadings have to be fixed to something for identification, and the others can be estimated. So I'm estimating the middle 2 because they're going to capture nonlinear change. They are going to become essentially what the new occasion would be at that point. It's like we're estimating time. It's really kind of bizarre, but it works really well. Go ahead.
Actually, I'm gonna
Keep listening. Okay. Well, we're about out of time. But we've got the fixed effects. The higher order intercept doesn't have a mean because it's imaginary. So that one's fixed. The slope factor does have a mean because that's going to become the fixed slope. We have an intercept variance and a slope variance, and we have a covariance between the two. So now our picture has grown. Right. Back out of that. Ta-da! This is what we had. So conceptually, it's like a trickle-down theory here. Here's my intercept factor. It predicts all of these 4 occasions. The factor at this occasion then predicts the 3 observed outcomes. So there's still a correlation pattern that is being implied by this higher order factor model. We're saying that the only reason that these lower order factors were correlated is up here. Up here is the G matrix, essentially. The intercept and slope factors are your new random effects. Their means are the fixed effects. Their variances are random effect variances. So this is G up here. The trident little pitchfork residual variances down here are for the indicators, but now we have residual variances at this level too, which is your R matrix. So this part is R right here, this part is G, and this didn't exist before. Ta-da! I think that's a good place to stop, don't you? Our heads are full. Oh, please stop talking. Yep. Just be thankful it's not a 3-hour seminar. Just saying. All right, questions as we wrap up this happy garbage day. We'll go back over this model next time too. It's going to take more than one shot to sink in. All right then, let's see. You don't have to work on anything right now, so just come back on Thursday, please. How's that? Let me know if you need anything. As a reminder, office hours are cut short to 3:30 tomorrow. All right. Peace out then. Thanks for being here. See you Thursday.